This is the first in a series of videos about integrated rate laws. We're going to talk about how integrated rate laws are different from the rate laws we talked about earlier in the chapter. We're going to do some examples using them for zero, first, and second order reactions, and then we'll look at a data set and find out how we can use integrated rate laws to find the order of that data set. So we have seen before in earlier videos about rate laws, and we used these to relate reactant concentration to the rate. But rate is kind of difficult to measure. It's difficult to measure what the rate is at any particular moment. It would be much easier if we could measure the time, and that's why we use the integrated rate laws. These were obtained using calculus, integrating each of those rate laws we looked at in the past videos, and integrating them with respect to time. So these integrated rate laws relate the reactant concentrations to time. A much more useful variable to measure. And so there are some new variables and some new tools that we use in this chapter, so I'm going to introduce them here before we talk about the actual rate laws. So we're going to be talking about concentration at different points in the reaction. So when we put a subscript 0 next to the concentration, we are talking about the initial concentration. And if we put a subscript T next to the concentration, we are talking about the concentration at time T. So if T equals 5 minutes, after 5 minutes have gone by, this is the concentration that is left. The other way you can think about the concentration at time T is the amount left at time T. So we started with some concentration, then some time went by and some of it was used up, and this amount is left. So that's what that variable represents. There's also a particular time that we care the most about, and that is the time when half of it is used up. And that is called the half-life. You may have heard this in reference to radioactive materials, because radioactive materials can be measured using kinetics. So the half-life, T1/2, is the amount of time required to use up 50% of the concentration. So the half-life is going to depend on the order of the reaction, so we'll talk about that as we talk about the rate law along our way. So now, as we proceed to the integrated rate law, we are going to use the following reaction. A goes to products. So notice that there is only one type of compound here and only one molecule of it. So only one reactant. We know how to identify the order of reactions that have more than one reactant, but when we start modeling them, they get a little difficult. So from this point on, we're just going to stick to reactions with only one kind of products. Now we're going to make a table, and that table is going to take an entire notebook paper page. So I recommend that you turn the page, as I will. And I've got my template started, so I will give you a second to copy down the template if you wish to do it in advance. Okay, so we're ready to start. We're going to talk about zero order, first order, and second order. And remember, the reaction that we're talking about looks like A goes to products. So A is going to be our only reactant. So let's start with the rate law, because that's something we've seen before. So the rate law always looks like rate equals rate constant K times the concentration of the reactants to some number. And since this is a zero order reaction, that some number is going to be 0. So rate equals K times A to the 0, or just rate equals K if you like it. So then if we integrate this, with respect to time, we get the integrated rate law, which looks like this. Concentration of A at time t equals negative k times t plus the concentration of A initially. This is the simplest of all the rate laws. And if you squint, you can see that this looks a lot like the equation for a line. This is a linear relationship. We can put the y here under the concentration of A at time t. If we plot x as our dependent variable, then we've got m for the negative k for the slope, and b for that concentration of A initially. There's a linear relationship between those two. So we can plot them on a graph, which is a very useful tool depending on how good your plotting skills are. So if we plot concentration as the y and time as the x, this is going to be a linear relationship, but there's a negative sign here, so there's going to be a negative slope. So our graph is going to look something like this. And technically you can't have negative time and you can't have negative concentration, so it will just start and end right there, and we'll ignore that part of the line that I just drew. And the reason that scientists bend over backwards to try and find a linear relationship between variables is because there's a couple of different points we can really easily solve for in a line. We can really easily solve for the slope, and we can really easily solve for the y-intercept. And so that's even more pieces of information we can get out of the graph without a lot of work. So the slope of the line, according to our integrated rate law for zero order, is going to be negative k. I may not have mentioned this before, but k is always a positive number. So if you have a negative slope, you want to take the absolute value of the slope to solve for k. And then here our y-intercept is going to be the initial concentration. So that's really useful. That's a really useful plot. And since we're talking about zero order, we'll throw in the formula for half-life while we're here. So T1/2 equals the initial concentration of A divided by 2 times K. And you can find this if you like by plugging in concentration at time t over concentration 0 equals 0.5. So if you plug that in for when 50% of it is used up, you can rearrange this relationship to find the half-life. But in case you don't want to, there it is for your personal use. And if we look at this, we'll notice something that's going to become relevant later. There is a concentration term inside this half-life. So this half-life is concentration dependent, meaning if we start with a different concentration, the half-life is going to be a different length of time. Okay, so that's the zero order or the zeroth order. So then we have the first order. You can write the first order rate law. So rate equals k times a to the first. And if we integrate that, we will get the following. Concentration of A at times t at time t equals the initial concentration of A times e to the negative kt. That's our integrated rate law. It has an e in it, an exponent. And this version can be useful, but there's another version that looks a little bit more like a linear relationship that we're going to use, because this is not a linear relationship. This is an exponential relationship. And I would really like it to be linear. So if we do a little bit more math and take the natural log of both sides, we can change the way it looks to be the natural log of concentration of A at time t equals negative kt plus natural log of concentration of A at time 0. That looks a lot more like the equation for a line, than this exponential one. It looks like y equals m is negative k again, t is x plus b. And I'll prove it to you with a plot. So if we made an attempt to make a plot the same as we did for the zero order with the concentration versus time, which is the way that we measured the data and recorded in our notebook, if we drew the plot, it would look something like this. It would look like an exponential, a negative exponential graph. And that's fine, but we really like linear graphs. And so we'd really like a way to be able to graph this relationship as a linear graph. And so the integrated rate law gives us a clue about how to do that. Our y term is natural log of a. So we know that if we take the natural log of a and plot that versus the time, then that should give us a linear relationship. And it has a negative in front of the t, so it's going to be a negatively sloped line. So it looks the same as this one, but the y-axis is different. The y-axis is the natural log of concentration. So we have to do a quick math transformation to make that work. And again, we can get useful information out of linear graphs. We can get the slope, which is equal to negative k, and we can get the y-intercept, which is equal to natural log of the initial concentration. So we can't get the initial concentration quite as easily. We can't just pick the number right off the graph, but we can pick the number off and we can take e to that number to undo the natural log to find it. And if we were to plug in 0.5 for that fraction of concentrations, we could find the half-life. And the half-life for first order is the natural log of 2 over k. And notice that this time concentration is not present in the half-life. So it is concentration independent. So no matter how much you start with, the half-life is always going to be the same. It only depends on the rate constant. All right, and our final order is going to be second order. So if this reaction A goes to products with second order, the rate law would be rate equals K times A to the second. And we could integrate that to find the integrated rate law. And we would end up with a fraction. 1 over the concentration of A to the T equals K times T plus 1 over the concentration of A to the 0. It's kind of clunky looking, but it is in the form of a linear expression, so we will accept it. The 1 over A is going to be our y. There's going to be a positive slope on the line this time. T is going to be x again, and then here's our y-intercept. So let's look at that plot of the raw data versus the plot of the linear data. So if we plot the raw data, we are going to have something that looks like this. It's going to look like a 1 over x type of a curve. And technically it does touch the axis at some point. My drawing is just sloppy. So this is fine, but it's sort of unhelpful. We can't pull the slope out of this. We can't pull the intercepts off of this. We want it to look like a line. So this is our linear relationship, and so we know we can find it by plotting 1 over the concentration times T, and it's a positive slope. So we're going to have a positive slope in our line. And our slope is going to be equal to K. And our y-intercept this time is going to be equal to 1 over initial concentration. So if this line hits the y-axis at 2, then the initial concentration is going to be 1 over 2. You'll have to flip it. And the half-life in this situation is going to be 1 over K times the initial concentration. And this one is also concentration dependent, just like the first one. So the first order is kind of special. It's the only one where the half-life doesn't depend on how much is present. So we're going to be looking at some data in the next couple of videos. And so the most important thing you can take out of this page of notes that we've made, besides the integrated rate laws, of course, is what you have to plot to find a straight line. Because if you plot concentration versus time and you find a straight line, you know it's zero order. If you make a plot of concentration versus time and you don't find a straight line, it could be first order or it could be second order. So you have to change what's on your y-axis until you end up with a straight line to identify the order. So let's just summarize that down here so that we can remember for future problems. So if we have a zero order, actually I'm going to do it like this. If we have a zero order, we will get a linear relationship for concentration versus time. So if we plot the data as it's given and it's already aligned, life is good, and it's a zero order reaction. If we have a first order reaction, we know the only way to get a linear plot is to use the natural log of the concentration of A, plot that versus time. And then for our second order reactions, the only way to get a linear plot is to plot 1 over the concentration versus time. So we are always going to be looking for the straight line in the data. If we can find the straight line, the axes will tell us about what the order of the reaction is. So we'll look at some like that in the next video.